Given this matrix M, K is a constant, and we're also told that this equation is true. A is a constant, I is the 2 by 2 identity matrix, and we're asked to determine A and K, essentially. So we've got M, we can quickly times through by 11, that's no problem. Let's work out what M squared is. It's going to be minus 2, 6, 5K multiplied by minus 2, 6, 5, 6K. Okay. So then I'm going to be doing the rows times the column terms. I'm going to get 4 plus 30, 34. Then the same row, but the next column, minus 10 plus 5K, or 5K minus 10. Then minus 12 plus 6K, or 6K minus 12. And finally, going to get 30 plus K squared. Great, so now I'm going to add on 11M. So let's take our time with this. We've got 34, 6K minus 12, 5K minus 10, 30 plus K squared. And I'm adding on minus 22. I'm just timesing this M by 11, 55, 66, and 11K. Bring this together. I'm going to get 12, 6K plus 54, 5K plus 45, and K squared plus 11K plus 30. And we're told that this is equal to A times I, so that's going to be A0, 0A. So straight away, we can just see that A must equal 12. And then I want to work out what K is. Well, let's go with another, I don't need to bring that quadratic into it. I could, but let's compare these two. Because we're given that it's true, so it's not like we have to check everything. So I can say now that 5K, just to show that, 5K plus 45 is 0. I think it's okay to go straight to our answer now. K is minus 9. And you could just check the rest of them. We could also have used the 6K plus 54 is 0. You get K equals minus 9. And then you could, I mean, I wouldn't solve the quadratic, but you could put minus 9 in and check that you get 12 and it will work. So we're there. Next up, we're asked to determine the equations of the invariant lines for the transformation represented by M. Of course, now I can replace K by minus 9. Right, so let's just remind ourselves about what an invariant line is. First of all, there's something called line invariant points, or just invariant points. And they are points that when you apply the matrix, you get the same point. Sometimes you get a line of invariant points. So for example, actually, here's a good example. Let's say we've got some axes and we were doing a reflection in the x axis, then all of these points would actually stay exactly where they are. Now that is different from an invariant line. So with an invariant line, it might look like this, for example. Now, every point, when you transform it, stays on the line, but it will, in general, I mean, it could stay in the same place, but in general, it will move somewhere else, but it will still be on the line. Okay, so that one they might like swap around or something, or they might just go all over the place. But that is what we mean by an invariant line. Yeah, and just to say again, a line of invariant points is an example of an invariant line, but there are other situations where they will actually move, and so you'll get other lines. Let's set up how to find it. We've got a value x, and then y is going to equal mx plus c. This is going to be my x on the line of invariant points. We're then going to map x to a new position, which I'm going to call capital X, and then my new y is going to become m capital X plus c. I'm going to get rid of that y there. So yeah, those are, we've got x and mx plus c as our x and y values. And this is transformed to capital X, normal, sorry, that should be a normal m times capital X plus c. That will mean that we stay on the line. And therefore, our equation becomes minus 2, 5, 6, minus 9, multiplied by this general coordinate or position vector, x, mx plus c, and that must equal capital X times m capital X plus c. And that is how we find the invariant line. So let's multiply out. We're going to get minus 2x plus 5 mx plus 5c, and then 6x minus 9 mx minus 9c, and that is equal to x mx plus c. So in fact, I can remove the matrix and just turn these into two separate equations. And then I can substitute in I can replace this x by this x here to get rid of one of the unknowns. Therefore, 6x minus 9mx minus 9c is going to equal m multiplied by minus 2x plus 5mx plus 5c, and then I'm adding c on. Let's multiply this bracket out. I'm going to get minus 2mx plus 5m squared x plus 5cm plus c. And then because this is true for all values of x, it's actually an identity, I can equate coefficients. I can say that 6 minus 9m, you could, for example, just substitute if you substituted x equals 0, then naturally you'd get rid of all of those and you could definitely equate the constants. And, then you could let x equal 1, for example. We know the constants are equal, so you could then cancel them out and you would get to this. This is another way of thinking about it. We're going to get minus 2m plus 5m squared, and oh, that's it. Okay, let me deal with this actually. I've got 5m squared plus 7m minus 6 equals 0. Just got an equation in terms of m. And this actually, it does factorize. 5m minus 3 times m minus 2 is equal to 0. Oh, hold on, sorry, m plus 2. Then we get 10m minus 3m sorted. So m is either going to equal 3 over 5 or minus 2. And if we take a look at the constants, I'm going to get minus 9c plus 5cm, sorry, equals, it should have been equals 5cm plus c. Therefore, I could write down that 5cm is going to equal minus 10c. So cm is going to equal minus 2. Now, don't just 2c. Don't just divide through by c, because we've got to think about whether it could equal 0 or not. So actually, what I could do is, there's two ways you could think about it. When I did it, I actually did this one first, and I said that either m is equal to minus 2 or c is equal to 0. That kind of then mapped with this. So if m is minus 2, c can be anything. And if m is 3 over 5, then c would have to be 0. Alternatively, you can get this equation and you can sub in minus 2, and then you would get minus 2c equals minus 2c, which shows you that c can be anything. Or we could sub in 3/5, and then you'd have 3/5 c equals minus 2c, and you'd see that c has to equal 0. But either way, we get our answer. Therefore, our invariant lines are going to be y equals minus 2x plus c for any value of c, or y equals 3/5 x. Brilliant. Right, it says state which, if any, of the lines identified in B consists of fixed points giving a reason for your answer, i.e. a line of invariant points. Okay. So the way I did this was I just decided to find the line of invariant points. I went back to the matrix, minus 2, 5, 6, minus 9. It is easier to get the line of invariant points because for any invariant point, it maps to itself. Rather than that capital X and M capital X plus C, just get this. So then minus 2x plus 5y is equal to x, and 6x minus 9y is equal to y. First one becomes 3x equals 5y, therefore y is 3/5 x. Okay, we can see it's going to be that second one. Let's just check that it's consistent. 6x equals 10y. So again, y would equal 6 over 10x, or 3/5 x. It's this one that is also a line of invariant points. Yeah, really like these sorts of questions. It's good using the methods to find both of them here. One of the way you could have done the last part would be to actually try each invariant line and check that you get the same thing, although I think it's pretty complicated. There is another method up here, and I nearly decided to go for it, but I think it's a bit unnecessarily complicated. So I'd say the way that I did it is a really good approach. Well done on this question.